A question that I get often from the audience is that if you were picked up and put randomly in the Milky Way, would you be able to find your way home? Would you be able to recognize the stars? And the short answer is probably not, but the long answer is maybe. And that just comes down to the fact that if you could see a few stars that you recognize, you could use the technique of parallax to be able to navigate your way home. And recently, the New Horizons spacecraft, which is well outside the orbit of Pluto at this point, was able to take a picture of the sky, compare it to a picture that was taken from the Earth at the same time, and the positions of the stars were different enough that astronomers could calculate where New Horizons was just by what it could see for the stars. And it's a fascinating idea. Now, my guest today is Dr. Tod Lauer. He's an astronomer with the National Science Foundation's NOIR lab, and he's a member of NASA's New Horizons science team. And he was the first author on a recent paper about how New Horizons had taken this picture and how they were able to calculate the position of New Horizons based purely on what it could see in the sky. But Tod is a legendary astronomer. He has worked with the Hubble Space Telescope. He was the principal investigator for his own mission and was a collaborator with the Event Horizon Telescope. And he is a master of taking pictures of space and figuring out things from that. And so we have a very wide-ranging conversation, not just about this result, but just Tod's experience in general using New Horizons as a space telescope and just how pictures are done in general. So if you are interested in the science of taking pictures of space, enjoy this conversation with Dr. Tod Lauer. Tod, I'm absolutely fascinated by this idea of navigating in space. And I actually get this question all the time from people, which is like, if you were dropped randomly somewhere in the Milky Way, would you be able to find your way home?
Yeah, that's a great question. And finding your way in the Milky Way, if you could recognize a star and you knew it was a certain star, you absolutely could. It depends on where you dropped me or, how close to home you were. It's like a lot of things. You have to know the territory. But if you were able to say, yeah, I know what the star is here, you're not so far away that, that's impossible. Yeah, you could find your way home.
And so what's the method that you would use? I mean, I think about Gaia, for example, and they've maybe mapped out 1%, 2% of the stars in the Milky Way, but there are a lot of very bright stars that are very far away
Sure,
that we can see with our telescopes. I don't know if you're on the exact opposite side of the Milky Way, behind the zone of avoidance. I don't know how far you'd be able to get.
You probably, because this is one of the interesting things about where we are in the galaxy. We're almost right exactly on the galactic plane. And so you have dust, that comes in, and you actually can't see the center of the galaxy in ordinary light. Infrared, you can see it. And, we can see, the center of the bulge, it's the brightest part of the Milky Way, but actually, in the plane, it's hard to see. So on the opposite side of the galaxy, Gaia wouldn't have been able to observe that. So there you're going to be a little bit out of luck right now.
Right. Yeah. Yeah. But you just aim towards the center of the Milky Way and then take your heading again once you're,
once you get through, yeah, you could give it a go.
Yeah, exactly. And so, and this is using the method called parallax. So for people who aren't familiar with that, can you sort of give a brief explanation of how you would be able to find your way looking at stars?
Well, sure. It's nothing fancier than the fact that, objects move as you move through them. Parallax is how you get depth perception. You have two eyes, they get a different picture of the world, from each of your eyes. And, the classic thing is, hold up a finger, blink your eyes, and wait, on the right, it's over there, but wait, on the left, it's, over there. What's going on? In fact, the coolest thing that I saw when I was a kid, and I didn't understand it, was we were driving on the road, past a cornfield, and there was a distant antenna tower, microwave relay or something, and the corn was moving, it was whipping past, and this thing was following us no matter where we. And I asked, what's going on here? And that's so the corn had parallax, and the tower is far enough away. It didn't. And that really made a big impression on me.
Yeah, it was like the moon. I noticed that with the moon when I was a kid.
Yeah.
That we'd be driving and the moon was always there, even though the trees were zipping by.
What's going on? The moon hasn't moved, but so is it staying with me as I'm going through all this stuff?
Yeah.
But the parallax is, where things are, or where you see them as compared to where you had seen them from another measure. And, what you know now, and you can see this, you land on a plane on a runway, things close to you are scurrying past you really quickly, and you look further away, you can see that lessening. And this is kind of what we use. You have to know what you're looking at. You have to know the stars. But then you say, well, how have they moved with respect to things more distant? And that is the signal that tells you where you are.
And so how much was this in the works? What was planned for New Horizons as a test of this?
Well, this was something well after the fact. It was a simple demo, and the purpose of New Horizons was to explore Pluto, which it did 10 years ago this month. And then 4 years after that, we went to Arrokoth as Kuiper Belt object, and that's the primary mission. And for spacecraft like New Horizons, you stay pretty much focused on that. You don't want to spend fuel or resources, anything away from, your main mission. But after Arrokoth, that's free time. We have a working spacecraft, and you can say, okay, we've done the mission. Now what are some other interesting things we can do? And one of the things that people always talked about was the fact we've gone so far that stellar parallaxes will be huge compared to what they are on Earth. And, some astronomers say, well, can I measure distances to stars that way? And you can in principle, but our camera isn't that accurate. It says low resolution and, it's not that sensitive. So, the further distance doesn't give us greater accuracy compared to, dedicated things you can do on Earth and around it. So we couldn't do that. But the demonstration of parallax is something we could do. And so we thought, let's just have a little demo. Let's just get a few pictures. Let's do the nearest stars, which we know have moved, and we can demonstrate, hey, look, parallax. But in any case, we did that 5 years ago. We demonstrated that we could see large parallaxes in two nearby stars, Wolf 359 and Proxima Centauri. And we picked these two stars to also do a navigation demonstration. And I regret to say, that sat in the back burner for a while. I said, we should get to this and write this stuff up. And so that's the 5 year later story. I said, okay, I had some time. Let's, trot it out and do it. But that was there from the start. But in terms of a demo, it was a very limited thing. We picked a couple stars. We did the observations to get them. It was a one shot, and it was made up, once we had leftover resources that we could do on interesting things, not in the primary mission. The thing that was very nice with New Horizons is we did simultaneous observations from the Earth and from the spacecraft. And that is exactly like holding your finger up and blinking the eyes. I mean, they tell you this in the class, but then you say, well, how do you really do it? Well, the Earth has to go around the sun. You have to wait 6 months. But while that's happening, the star is drifting through space. And so you have that on top. So you have to observe a few years, and you look for this wobble back and forth as it's moving, but it's very small. So you have to do precise measurements. And here's some numbers we measured to demonstrate that the star had shifted. With New Horizons, we instantly could see that the stars have moved. We put the pictures side by side. It's there in this picture, there and that. That couldn't be any clearer, and it couldn't be any more simple. So we hope, I don't know if this will be realized. Our fondest hope is that in basic textbooks, when they talk about parallax, they can say, hey, you can see it, with New Horizons and the Earth. It should be a great demo. We'll see how that plays out.
Right. Yeah. Yeah, it definitely is. And so essentially New Horizons looked at a spot of the sky, and then Earth-based telescopes looked at the same spot of the sky
at the same time,
and then took a picture, and then you could just blink compare the two spots in the sky and watch as stars are jumping back and forth between those two positions. It's exactly the same as you opening and closing your eyes with your thumb out and watching your thumb jump back and forth.
It is, and there's something else you can do, and we had a little help from Brian May with this, is, you put the images side by side, and if you view them simultaneously, just like your eye uses parallax for depth perception, you can see the stars, their target stars, pop out in front of the background stars. So it's however you want to look at it. Do you want to make a jumping back and forth thing? Actually, I find that easiest. Or do you want to put it in a stereo viewer and see it? I mean, these are some of the things you can do.
Yeah, that's an astonishing effect. And I've, there's these really cool sort of magic eye things you can have where it's like two pictures side by side, and then you sort of unfocus your eyes at the right way, and then the differences between the two images will float up and hover in front of you. And so there's no special trick being done with these two fields of stars. You're just looking at them with two eyes side by side, and then you kind of unfocus your eyes, you do this trick, and then you'll spot Proxima Centauri or Wolf 359 hovering above the rest of the star field. And it's just this parallax method, because literally your brain is doing its job, showing you the star that's closer.
With one eye on Earth and one eye on the edge of the solar system, a little far apart. That's a rather big head, but
but the trick works in exactly the same way that it works. Just as we walk around and live our lives, except as you say, one eye is on Earth and the other eye is a telescope on a spacecraft that is very very far away beyond the orbit of Pluto. Oh, absolutely fascinating. So then, what kind of accuracy did you get from this?
Well, the accuracy was interesting, sort of 0.5% in distance. So, that's 1 out of 200. So that's good enough to say, here we are. And, when we plot it up on a figure in a paper, the error is about the width of the plotting line. So that's pretty good. Now, it's well away from what NASA's Deep Space Network can do or what Gaia can do, and both of those are profoundly precise. So, we're not looking to, put them out of business. But at the same time, it was good enough so that on a figure, here we are, So, and best of all, we, plotted our answer, compared to the Deep Space Network trajectory that we had. And, they hit each other right in the money.
A question I get a lot from my audience is, if there was a new Gaia, would there be value in putting a Gaia out at the orbit of, say, Pluto?
No, it turns out, I remember I thought about this, and it goes way back. I heard of all things from Freeman Dyson's son 5 years ago. He had thought about this, in the 60s. But this will sound really funny to say this, that only buys you a factor of 100 or so if you do it right, but it's only in a particular direction. And Gaia was so good, it was like orders of magnitude. It was like a factor of 10,000 better or something than what we could do. So if you have money, how you spend your money, it's making more accurate instruments on Earth rather than putting less accurate ones far away, because that's a long way to go. The telemetry is really, really hard to get. I know how, it is to communicate with New Horizons, and around Pluto, the speed was like an 80s dial-up modem. That's pretty thin. And so operating it, controlling it, powering it, all of that is going to undo that. And you can just do more accurate by putting the money for a deep space mission into something closer at home with more accuracy.
Yeah. And not to mention the amount of transmission that you can send home.
Oh, it's very difficult from the outer solar system.
Yeah. The closer you get, the faster you can get your data home.
Oh, yes.
Yeah. So then, let's imagine that you took New Horizons, you you closed its eyes, you spun it around, and then you moved it somewhere randomly in the solar system and then woke it up, would it, and it was allowed to ask for pictures from home, would it be able to know where it was?
Yeah, and actually, you wouldn't even need the pictures from home. There's a little sleight of hand here for the parallax demonstration, where we just wanted to show parallax. We took simultaneous images from Earth and New Horizons. But for the navigation experiment, we didn't need the images from the Earth. We used the Gaia catalog instead, and Gaia says, hey, here's where everything is. So, and it's beautiful accuracy. It's reduced to the barycenter of the solar system, so there's no parallax of wobbling back and forth, just even on a small scale, and all the things you have to think about when you're on the Earth. So you could, with New Horizons, we don't have the software, but with the catalog on board a spacecraft similar with a good camera, yeah, anywhere in the solar system, you could figure out where you were.
How accurate do you think? Yeah, how accurate do you think? Like, could it be accurate? Like, I know that with the spacecraft that are in the outer solar system, the communication delays are pretty
Sizable,
serious.
Yeah.
And that if the spacecraft could figure out where it is and orient itself, maybe in time that has to do some kind of burn, are these the kinds of things that we could have them do autonomously?
Yes, absolutely. And I have an exception to this that I have to mention, but yeah, you can. It depends on the quality of your camera. New Horizons camera is rather low resolution and not incredibly sensitive. And some of the cameras that we've flown to Mars, for example, would be more sophisticated. There's talk about a Pluto orbiter, which would have a 1 meter telescope on it. Things like that would just, blow our camera out of the water. So you can make it much more accurate. And, our error was, sort of like a few tenths of an astronomical unit. And that's about where we could get, I think, with, a more sophisticated camera. Now, there is another method that's been proposed, which is spectacularly accurate, and that's doing timing in the X-ray of X-ray pulsars. And that has been demonstrated in Earth orbit, and it's proved to be very accurate. And people are talking about putting that on interplanetary missions. So again, you could be autonomous, and that may be the way it goes. The problem there is, though, that you have to have specialized hardware, which is always a cost, mass, power, complexity to put on, a mission if you don't have a cause for it. Whereas with New Horizons, we used the camera we got, and so we didn't need anything special. That's the advantage of what we have. How people would do this for real, I truly don't know. But, autonomous operation is something that people would like to do, put the spacecraft out there so I don't have to mess with it all the time,
Yeah. I know that experiment, I forget which one it was, whether it was the NICE or the ACES experiment on the ISS, got it down to like within 100 meters or something. Like it knew exactly where it was.
That's right.
And that those, both the X-ray pulsars and even just the radio pulsars, they give you a fantastic map. I mean, Carl Sagan put them on the Golden Record.
I put it on the Pioneer.
On the Pioneer plaque.
Yeah. And I remember the pulsars radiate. This is where we are, and it's really accurate. So
yeah. So if you really want to navigate, that's another way to go.
But we had no axe to grind with this. This is what we could do. What value people will get out of this, or will go somewhere, I truly don't know.
Yeah. I mean, and again, I sort of like this romantic notion that the spacecraft, if it had the propellant and it could survive long enough, could navigate itself all the way to Proxima Centauri.
Yeah.
Yeah. Just keep it in the crosshairs. So, using New Horizons, which, as you say, doesn't have an enormous telescope, doesn't have a giant camera. It's no Vera Rubin, but it does have a unique position in the solar system, that it is outside of the gas and the dust and has a very pristine view to the cosmos. So what kind of astronomy can be done with a telescope that far away from the dust in the solar system?
Well, this is something we've tried, and whereas the navigation was a fun demo, a real scientific investigation is something that we did try with the camera aboard New Horizons, and that was to measure how dark space is. It's an interesting thing. I mean, with big telescopes like the Webb and the Hubble, you can count up very, very faint galaxies, and you can look back to when they were first made. You look all the way back to a little bit after the Big Bang, and you can see all the stars that they made. And the question is, though, are you missing anything? Is everything associated with galaxies, or is there another source of light? And with New Horizons, we can barely see the nearest galaxies, but it's extremely dark out away, in the outer regions of the Kuiper Belt. There's hardly any dust. We're getting away from the city. The sun lights up all the dust, in the inner solar system, and even the Webb and the Hubble, have to look through that. So we had a dark vantage point, which is unique to anything ever done. And so we just simply said, how much light are we getting from the universe? And we had a very accurate measurement. People have tried this for decades, but you do it around Earth, you have to correct for this, you have to correct for that, and so on and so forth. And we just were able, by being so far away, to do it much more accurately than anybody had done it before. And we came up with this, I hope is an interesting answer, which is that we see pretty much just what the galaxies are within our errors. I mean, our number, allows for a little bit more than the galaxies, but not with high significance. But we have enough significance to say whatever is out there, most of the light we're getting is from galaxies. And so that's called the cosmic optical background. And that was a substantial effort that we did in the last number of years. And that has proven to be very, very useful.
And one possibility would be that maybe there were sources of gas that was in between these galaxies, or dwarf galaxies, things that weren't visible because of all this obscuring light?
Well, one of the things, depends on how exotic and speculative you want to be. A simple thing, which I think we could be very useful for, is what's the fraction of stars that have been tossed out of galaxies? We know when you see simulations of merging galaxies that they have, they throw off stars in these big loopy tails and things. And we know in clusters of galaxies that there are a lot of stars that end up, in the cluster, just like a sea of stars. It's very faint with the galaxies moving around in it. So for the whole universe, there must be, some level of stars that, is swimming around with, hey, what happened? We're not in our galaxy anymore. And that we can constrain. And that's a question which is still alive. I've asked some of the people that do simulations, what do you see in terms of what's being thrown out? Is that consistent with what we see? And, it's not a question that so far has produced an answer theoretically, but yeah, we can do something like that. Now, there are more exotic things like, what's all this dark matter stuff going on, and does it decay and does it emit visible light when it does it? I can't answer that, but if you have a prediction on what it does, that will be in our budget. So we can say, here's the money you have to spend. This much of it is on galaxies. We'll give you this little bit left over. That's what you got to work with. If somebody says, oh, I can explain the whole brightness of the universe by decaying dark matter, is like, it's not that bright.
Right. So if someone had proposed a theory that, say, dark matter was going through some kind of self-annihilation back when the universe was more compact, then there would be an increased amount of radiation that you would detect in between galaxies, wherever the dark matter was concentrating.
Sure. Yeah.
And we don't see that kind of radiation. And so that puts a lower bound on, or an upper bound, it puts a bound on where the astronomers, if they're predicting some kind of particle behavior, they have to constrain it. But wasn't one of the other things to sort of give us a sense of just how many galaxies there are in the universe? I know that the estimated number of galaxies had changed a bit, now that we could see, in fact, what we see is what there is, as opposed to there being more that we weren't able to see.
Well, yeah, we can't count the galaxies ourselves. And that is a primary task for both the Hubble and the Webb telescope. And the Hubble has done it very well for, the duration of its mission. And one of the things which is interesting to us, when we took the Hubble observations, the work that other people published, there are many people who tried it, and they actually agree pretty well on how much light comes from galaxies. So we've got that, and so we can check on that. You say, okay, well, sure, you've counted up the galaxies, we can't see them, but you can say how much light comes from those galaxies, and that we can check on. So we can't say how many galaxies there are, but we can say whatever you do, it has to fit within this limit of how much light you get.
Now, you spent a lot of time working with the Hubble Space Telescope. That's probably the mission that one of the best. And now we're in sort of the age of Webb, and the discoveries are coming fast and furious. Are there outcomes that you have been hoping to see, the stuff that was like just beyond the limits of Hubble, that now are within the capabilities of Webb, and either we've seen them, or hopefully someone is going to run the survey, run the Webb deep field to give us the answers?
Yeah, and I have to say I haven't followed that as closely as I should. The thing about the Hubble Space Telescope was we wanted to reach back as far in time as we possibly could, and with the Hubble, that's pedal to the metal, throw everything you've got, do the best you can. The Webb was to make that problem a lot easier. And so my hopes were nothing more than I think what a lot of astronomers were thinking. I had no particular bets on the table or anything like that, or theories. I'm not a theoretician. I didn't say, oh, it has to be like this or that. I just wanted to see the answer. I just wanted to see what happened. And there it absolutely looks like the Webb is living up to the billing. There are some surprises by the people that have more sophisticated understanding of what's there than I do. And that's always good, because it says, you don't know everything yet. This is exploration to learn, and this is pure observation. I'm not out to prove this or that theory. I just want to see what's there, and it's working quite well for that.
Mm-hmm. I mean, I know a lot of those just basic fundamental questions that Webb was given. How did galaxies come together? When were the first, when did the age of, I guess when we come out of the dark ages, when did we see, when did those first supermassive black holes, quasars turn on?
Yes.
All of that kind of stuff we're seeing.
Yeah. Yeah.
And stuff we no one expected, like these little red dots and other interesting structures.
You have to be a little careful with those things. And I've seen this with a lot of missions. The data presents itself in unusual ways that you may not have anticipated. But when you go back and you do your homework, you say, oh, yeah, that works within this understanding. It's just, with astronomy, it's the difference between astronomy and physics. And physics is the fundamental principles. In astronomy, you mix in gas and dust and radiation transfer, and things get pretty messy. And, sometimes you say, oh, yeah, wait, I guess we forgot to throw that effect in there. I think if you don't mind a little digression, a lesson I got, which is very powerful to me, was the first time Voyager 1, went to Saturn. and, got images of Saturn's rings, and they were braided, they were broken into a phonograph record, there were waves, there's all this stuff. And people's like, oh my God, must be physics we don't know, and, blah, blah, blah. And it turns out it's ordinary classical physics, just in the circumstance. And somebody said at the time, so calm down, everybody. Let's, get out the textbooks, go through this stuff and see what really happens when you make a system like that. There's things you didn't think about. And that turned out to be true. You learned a lot about how these things work. Nature is a lot richer than our imagination, but, it was not new physics, just physics in a new place that you didn't understand before.
Right. But new physics would be pretty exciting too.
New physics would be pretty good, but for me, frankly, it's great when it comes along, and typically I expect, like a particle accelerator will say, hey, what's going on here? I think, before you say, oh my God, new physics, you have to do an awful lot of homework to be sure, and a perfect example there was the pioneer effect, the fact, and this is close to back onto, interstellar spacecraft. The pioneers, which had exquisite tracking from the Deep Space Network, had this acceleration which could not be explained by gravity. And so, is this a fifth force? Is this new physics? And people took years and efforts to run it down. Ultimately, it was like, oh, it's heat radiation coming off the spacecraft asymmetrically, being like a little rocket. It was painstaking work. It was incredible. But that's, you have to do that level of homework before you sort of, reach for, oh my God, it's new physics.
Yeah, it was interesting when Webb first sort of came online and started to make some of its early observations. There were a lot of these claims about the farthest galaxies that have been seen so far, and they were being seen at Z numbers of 16 and 18, and people were going through all of these sort of breathless, excited announcements and sort of claiming that they'd found the farthest galaxy. And then all those numbers got ratcheted back down. And I think now we're in the 14s.
Yeah,
and yet right. The good spectroscopy data have actually been taken at these galaxies. And so people are very comfortable that, yes, indeed, we are seeing these galaxies at 330 million years after the Big Bang, which is still very exciting. I mean, that's incredible to see a galaxy that old.
It's incredibly exciting, but, as they say, the easiest person to fool is yourself. And so, I don't criticize it. It's very exciting to, have your hands on a new instrument and see these things. But, you do have to check your math, and could it be this? Could it be that? It is an art. Frankly, it's an art to decide, how well do I understand this? When do you publish and say something? If on the opposite side, you wait till you know everything, and that this is checked out, you'll never say anything. So it's a trick to know, how confident do I have to be before I say, hey, I think I got something.
Yeah. I mean, I definitely watch the conversations go back and forth as astronomers make announcements, and then other astronomers are dubious or skeptical of those announcements, and it sort of puts the conversation out in the open. And I always wonder, was it better to open with that announcement before you had made it clear? Or if everybody's just if everyone can put their egos aside, then it can be very entertaining to watch this unfold in real time as people go back and forth. And as long as they're all working with a common good, they get to the right answer together in a way that would be a lot harder for people who are toiling away. But often egos do get bruised. People do get a little grumpy with each other.
This kind of thing is something that takes, your whole career learning how to perfect this, and every scientist, approaches it differently and gets a different answer. I think the thing which is true, though, is it's important not to do something stupid. I mean, make an elementary mistake. You say, "Oh my God, you it was really a red filter, not a blue filter. Oh, that makes it really different." That's a stupid mistake. But on the other hand, there are sometimes subtle mistakes, and with a new instrument like the Webb, you want to inspire future work. You want to bring things, and you have to say, "This is what we see. It's provisional." Tell it, and you may be wrong, But if you've done due diligence, you're not going to be drummed out of the core. People will respond. It'll be stimulating work and say, "Oh yeah, we checked about that. Didn't play out, but it was a worthy avenue to think about." So that's the art with it. If you wait till certitude happens, you're never going to say anything. It's the way it was. Everybody's calmed down a little bit with the web. It's going to be a great machine for discovery. We don't even know. It's early in the mission. Quite, and people get excited. That's great. It's what it's all about.
If I was to, I don't know, like write down the answer to some fundamental question that you might have about astronomy, and then pass it over in an envelope, and you could open the envelope. What is a question that you would just love to know the answer to that may or may not happen within our lifetime?
Where is the nearest technological civilization?
Yeah. It's mine too. That's funny. Yeah. I mean, I feel like it's the most profound question humanity can ask. Are we alone in the universe?
It's actually, when I tell people an astronomer, that's typically the first question they ask, is anybody out there? And so I would love to know that answer more than anything.
What's your most satisfying answer to the Fermi paradox then?
Well, mine actually, and I'm kind of a minority about this. I don't think anybody's out there, or if they are, I think it's very, very rare. I grew up on Star Trek and Sagan, and I admire Sagan's ability to communicate and inspire people. All the science fiction, right? But in a non-sentimental way. Fermi's argument is very strong. And oddly, a lot of the answers, the alternatives, are actually incredibly depressing. Like, well, yes, the universe is full of life, but all civilizations will destroy themselves in a century. Well, that's a hell of a note. I mean, I'd rather take, nobody's out there than, we're all condemned to destroy ourselves with complete certitude, or it's impossible to travel between the stars. I mean, there are a lot of excuses that you can make up. And I think the simplest thing is Fermi's, insight that, if we're rich in technological civilizations, somebody sooner or later, would have spread and radiated. It may be very uncommon, but the more civilizations you have, the more you have to tighten the rule books to say, yes, but none of them ever did this thing. And that gets harder and harder.
Yeah. And as we sort of began the conversation, if we gave New Horizons a better fuel tank, it could make the journey.
Yeah.
And maybe a 3D printer to make more copies of itself, and then it's off and running.
As an aside, I can't resist mentioning this. If you ask me which scientist in the past would I like to meet, it would be Fermi. I had the privilege of knowing a number of people that work with Fermi, and to a person, they just said he was a scientist, and more than the others, I would have loved to have say, hey, would we like to have lunch with Fermi with his brown bag and to kick some of the stuff around.
Yeah, that'd be amazing. Tod, what are you obsessed with right now?
That you told me you're going to ask that question, and I didn't, in the background submit a job, so that
didn't prepare.
Brain to come with an answer. I will tell you my career-long obsession, is I am on the imaging side. My challenge has always been getting, the most and the best information out of an image to answer a question. And they say that's not necessarily the same thing as making something which is pretty to look at. But, an analogy I have, and these are expensive instruments. It's like getting to the best, restaurant in the world, and you've waited for months to get there, and you go there and it's expensive, and you got this menu, and if you order well-done burgers slathered in ketchup, I mean, you have missed the experience. And so if I get data that's worth billions of dollars, and, in some sense it is, understanding how to push the instrument to its limits, but not a step beyond, is a challenge. And that's actually how I got involved in New Horizons. Was they, were going into Pluto, and they were very concerned about, hitting something on the way in, because they discovered all these satellites around it, after they launched. Who knows what would be there when you got closer. And so they had a reconnaissance effort, and the problem was that Pluto was in the center of the galaxy. It's the richest, most crowded field of stars in the sky. And their camera was low resolution with blocky pixels. And it turns out they do not have, New Horizons is controlled by thrusters. It's not fancy reaction wheels like, the Webb and Space Telescope has. And so it jiggles around and drifts a bit. So the blur function changes from exposure to exposure. And now, find in that morass, find a little tiny thing that doesn't belong that you might run into. And for me, that's like, oh yeah, that sounds like fun. But that's how that's how I got involved in the team, was, talking back and forth. Well, I think you can try this, this, and this, And so my obsession, as it were, is, has always been, extending human vision, as it were, with the new instruments, and finding out how do you get out the story, that they're telling in the way that really makes the most, really it uses the full capability of the instrument.
Yeah. And often those techniques aren't figured out until even after the spacecraft is flying, I think of a recent example. They figured out how to use the Mars Reconnaissance Orbiter that's got a ground penetrating radar system, and they were able to roll the spacecraft and realized that by rolling it 120 degrees, they were able to penetrate deeper into the surface of Mars. And this is just something they hadn't realized, that it just got better the more they rolled it.
There's a lot of things with something that, I think has not gotten the press it deserves, was the Cassini mission, where they had the radar instrument, which they used to probe Titan. And they looked in the data, and they found echoes, off the main surface. And it turns out that they were getting reflections from the bottom of, basins of liquid hydrocarbons. And it was incredible. They were able to do soundings and map out below the surface of where the fluid was. And it was incredibly clever stuff. And that's exactly the thing that's like, oh, that's really cool. Let's make use of that. And the one thing that I would add, though, is often, there is a whole mathematical theory behind signal processing. And that's stuff that I like to think about, as opposed to saying, oh, well, I'm going to make up this thing because it looks good. Often there's a very solid understanding mathematically of how that goes. And that comes back to the stuff with the Event Horizon Telescope. Bayesian statistics is a mathematical discipline. You may not like the answers it gives, but, you can describe exactly what it's doing, and it's going to produce something very powerful if you can use it correctly.
Wonderful. Well, Tod, thank you so much for taking the time to chat with me. Let us know when New Horizons has found its way to Proxima Centauri.
Yeah, I think it's going to be a little while from now.
50,000 years or so. Yeah. Awesome. All right. Thank you so much.
Thank you.
I hope you enjoyed this conversation with Dr. Tod Lauer. Now, we had a much longer conversation. Actually, it was like a lot longer. And we talked about his experience working with the Event Horizon Telescope, that he helped contribute a bunch of ideas that then went on to give them a much better idea of what it is that they were looking at. And so if you want to hear more sort of behind the scenes about the Event Horizon Telescope, you can see that conversation over on Patreon in our Interview Plus version of this episode. As always, It's completely free, freely available. You don't have to subscribe to anything. You can just go over there and watch it right now. I'll put a link in the show notes. All right, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Barely Griffing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Balok, Cy Nelson, David Gilton, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hudson Ward, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Modso, Paul Roebuck, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. I'm always fascinated when I talk to astronomers about this balance, this dichotomy between, like, when do you take your conversation to a wider audience? When do you talk to other scientists about what it is that you're working on? How do you balance between making sure that you have done a really good job of taking a picture, and when are you maybe a little out over your skis, which is, I don't know, is that a Canadian expression? I don't know. And it was really interesting to hear his perspective on that as well. And I know that there's sort of that comes into the tension with what the public wants to see. You know, the public provides the taxes, the funding for the work that the scientists do. The scientists are expected to learn about the universe and the cosmos and to share those results with us. And yet the incentives can get kind of mixed up and mashed up. If you're expected to do everything transparently, then it's really hard to take the time to think about your work in a way that allows you to do the best work. And yet, if you spend too long cloistered just staring at your data, you may be missing this outside feedback and perspectives that could be really helpful to you. And I think Tod described it beautifully, that there is this wisdom that you will spend your entire scientific career trying to figure that answer out and reaching this place where you live perfectly in this tension between trying to make progress in a way that is very efficient for you, but also taking advantage of this collaboration, these other astronomers or scientists that can't wait to pick apart your data, but also to help you improve what you're doing. And the conversation goes on. All right. Well, I hope you enjoyed this conversation with Tod Lauer, and I will see you next time.